First of all, I want to thank you all for putting your valuable time and coming here. My PhD research will be about monitoring, control, and optimization of energy infrastructures. So, as you have seen in my perspective, my research will consist of two parts. The first part will be about controlling and optimization of the drilling process, and the second part is about advanced deep water monitoring system. So for each of them, I will present the introduction, and then I will present my preliminary results, and then I will talk about my future plan. So the first part about the control of the drilling process. First of all, I wanted to talk about several types of drilling. We have lots of types of drilling, but I just mentioned some of them here. So in conventional drilling, usually they insert mud into the drill string, and the mud comes back from Annulus and to the mud pit, but it is here the pressure is atmospheric. Then they have made managed pressure drilling, and they added a control valve here, and they seal the Annulus so they are able to control the pressure here, and this way controlling the pressure is easier. And also we have dual gradient drilling, and it is one type of managed pressure drilling. And in dual gradient drilling, instead of that mud comes back through Annulus, it comes back through a separate riser to the sea level, and in this way they are able to increase the difference between the pressure of the wellbore and the pressure in the formation, so it becomes more safer. And we have also underbalance. Another type of drilling is underbalance drilling. So usually in drilling process, they try to keep the pressure in the wellbore higher than the pressure in the formation, so they don't let the mud to come inside the Annulus. But another type of drilling is underbalance. In underbalance, they try to keep the pressure in wellbore a little less than the formation. This way, they don't let the mud flow rate to go inside formation and damage it. But it is a little more dangerous, but it is advanced. Another type of drilling is the directional drilling, and it is being used for mostly drilling horizontal wells. So in the literature, so there are lots of types of, again, models for downhole pressure. I tried to put them in several categories. One of them is one-phase flow. They basically just assume that everything in the Annulus and the drill string is in one phase. So they have their own mass balance equation, and they derive the model. And it is widely accepted in industry and also in the literature. And there are like papers comparing its results with some industrial plants, and they reported it captured the dynamics. But another type of model is two-phase. They assume two-phase inside the thing and Annulus, and it is a little bit more complicated, but it is highly, again, simplified. Another type of model is detailed model. It just consists of partial differential equations, and this, like, because the researchers do not have access to industrial systems or experimental systems, they usually try to compare their results with detailed model results. Another type of model is empirical, that they drive it using experimental data. So these are, like, here I just presented one-phase flow that I have, so far I have used this model. So we have three state variables, and this is nonlinear because of this part that we have flow rate squared. And also in the drilling process, the Annulus friction factor and also the density in the Annulus, both of them are unknown, and because they change with as they drill. So these two need to be estimated. And also after estimating the pressure through the drilling bit and also the Annulus, the density and the friction factor, they can estimate the pressure of the bead. And we'll talk about it more later. So again, most of the researchers have had mud pump flow rate and the choke valve opening as their manipulated variable. And for their control variable, they try to control the downhole pressure, and usually they wanted to estimate the friction factor density and flow rate through the bead, and then they estimate the downhole pressure. So again, into dual gradient drilling, they have another pump that is C pump flow rate. They have it at their manipulated value. So again, there have been lots of types of controllers in the literature. So most of them were linear controllers, but some researchers have had nonlinear controllers too. For their observers, most of them have used uncensored Kalman filters or adaptive observers and other types of observers that they develop themselves. Here in my research, we will be using multi-phase controllers and also nonlinear optimization-based estimation as our observer. And both of these will be optimization-based, and both of them will be using either active step method or interior forms method for optimization. And also, I will be using simultaneous approach in our software APMonitor, and here this is just a result that they have implemented it on a system, and here you see that simultaneous approach has much less computational time than the sequential one. So again, in this project, we will be using wire pipe technology. And wire pipe technology is a new technology, and here they put wires and special types of sensors inside the pipe. So this way they are able to measure the pressure along the annulus, because like up to now the sensors that they have, they aren't capable of being used for control purposes because they send limited bandwidth signals. But this new technology enables us to use these sensors for controlling pressure directly. And we don't
go on to the next slide. I want to give some perspective on the communication rate in drill strings up to this point before wire pipe technology. You see mud pulsing, and you see the data transmission rate on the y-axis there. And look at the data transmission rate in bits per second up till this point. Okay, and so what is it's maybe about 40 bits per second we've been able to do with mud pulsing, and now they're able to get megabit connections down to bottom hole assembly. So one of Riza's kind of main contributions to this work is how do we exploit this new communication link, and that's very very significant. Right? IntelliServe is actually based in Provo. It's a new technology we just came out with. So excited work.
Everything is a fiber optic connection.
No, it's not a fiber optic. It's a coaxial cable that they embed into the drill string itself, and then induction connections where it screws in together on the bottom left of the picture, so you can maintain that connection.
It's really not fiber optic.
Yeah. Okay. Yeah. This is not.
So that is what is the big change. Sorry to interrupt.
Yeah. No.
I'm just curious what caused that huge. I mean, orders of magnitude jump where we've seen an order of magnitude jump over a few decades. So what was the main driver?
I'm not that much aware of the hardware part, but I know that like from software point of view, the bandwidth increased, so we can use that as control purpose. But I also know that they have some special types of wires in the pipes. So when they connect the pipes during the reading, these wires can go attach together and send the signal through that to the reading rig. That's what I know about.
Better connection of the wiring.
Yes, because so when they drill, they have a drill string, and as they drill more, the second part comes and connects to the previous part, and so this way both of these parts have wires inside them, and when they attach together, these wires attach together, and then they are able to send the signals to the rig.
Provo company that developed this technology, so we're kind of in a unique position here to it's a joint venture between Annulus and Schlumberger, both multi-billion-dollar companies. It's sort of JV between the two. Yes, Schlumberger is a 45% of it. Not so much. There's a big artificial diamond industry here, so that's kind of the tie-in to the Mega Diamond and US Synthetic is those other companies.
Okay. So again, here in my project, I will be using rate of penetration. So rate of penetration basically is just define the length that it real divided by the time, and it depends on so many variables, and they are considered either controllable or environmental variables. Controllable variables are just we can change its value as we like to affect on rate of penetration. Environmental variables are those that we can change it. For example, like the drilling bit type. There have been lots of types of models have been presented through researchers. I don't introduce them here, but most of them are empirical models. But the one that is widely accepted, especially in industry, is the one proposed by these researchers. It's an empirical model that it depends on our variables that I will be talking here. So in this it says that ROP, which is rate of penetration, depends on some environmental variables. So here environmental variables are the properties of the formation and also the controllable variables. So far, researchers have shown the pressure as environmental variable, but we will consider it as control variable also here. So it depends on the downhole pressure, and ROP also depends on the weight on the drilling bit and the rotation speed of the drilling string, and also two spear. And so these three will be our control variables. So I present the results that I have had so far here. I used reduced order model for bound phase flow, and I used model predictive controller using API solver, which is the active set optimization solver, and I have used nonlinear estimation again using the API solver. So I assume we have multiple pressure sensors along the both drilling string and Annulus. And also, for this project, I used MATLAB Simulink and APMonitor together. So this is like the structure of the drilling rig that I have modeled. So for my manipulated variables, I have the pump flow rate and I have the chuck valve opening. And for my control variable, I have the downhole pressure here. But for now, I'm assuming that it is I'm controlling it directly. We have measured variables along the drill string and the Annulus, and also I have estimated variables that I'm estimating the friction factor inside Annulus and also density inside. So this is the structure of my controller. So I have my drilling well, and inputs of it is the pump flow rate and chuck valve opening. And it gives me the pressures along the drill string and Annulus, and these pressures along with the manipulated variable coincide estimator, and it finds the values for Annulus density and also Annulus friction factor, and they go as input inside controller with the pressures again, and controller decides the best manipulated variable values. So this is again the results I had, and I let it run for some time to make sure it's become a steady state. So these are the changes of the manipulated variable over time that the controller has reported. And these are the trend of change for my pressure. The purple one is the borehole pressure, and the others are my Annulus and also the drill string pressures. And here is the friction factor that has been estimated. And because now I have several pressure sensors along Annulus, I can estimate several different friction factors along Annulus, because so far researchers have just one friction factor estimated. And it will be helpful during like some unwanted And also this is the density in the Annulus that it has been estimated. So for my future work, so I will be one of my goals is to combine the pressure control and drilling rate control together to take advantage of stuff. This way we will be having more manipulated variables. So also for my project, I will be using wire drill pipe technology. So far, I have just had 5 pressure sensors, but I'm looking to add more pressure sensors. So as they drill more, the number of pressure sensors will increase to make it more realistic. And then I will use optimization-based approach, and I will be adding some fault tolerancy like like the tolerance for kick, managing the kick, and also stick slip condition if I have time for it. And here again the variables that affect on the downhole pressure and rate of penetration, like my manipulated variables. Usually the researchers have had these two as their manipulated variables, and they affect on the downhole pressure. But for rate of penetration, they have had real-time optimization approaches. And rate of penetration depends on weight on the drilling bit and rotation speed. But if I can combine them together, I can affect on rate of penetration from downhole pressure, because the less the downhole pressure, the higher the rate of penetration would be. And I can affect on downhole pressure through changing the rate of penetration. Rate of penetration itself has less effect on downhole pressure, but changing the rotational speed of the drill string will highly affect on friction factor. So we will be able to estimate the friction factor more precisely and affect on a downhole pressure. And advantages of this project is drilling in more challenging formations for sure, improve rate of penetration, improve operational safety, and drilling more efficiently and controlling the pressure more precisely for sure, and using this, taking the advantage during unwanted events. And the challenges that I will be having, one of them is that my rate of penetration model is highly nonlinear, so optimizing it will be challenging. And also, rate of penetration model have constant itself. So I should either estimate those constants, or I should just assume that they are known. So because like researchers have had some optimization-based approaches to find those constants. And also ROP model is empirical model, and I prefer it to be first principle, but because the relationship isn't completely known, researchers go to empirical methods. And again, I will be using one-phase flow model, but it would be better if I can have more complicated model that can capture the dynamics better, although this is reported to be a good model for me. And linking the two models will be another challenge for me. And for peak detection, I need to estimate more variable, and it will be, again, enforce some uncertainty in my work. Again, my contribution will be comprehensive controlling the rate of penetration and pressure. So I have seen some industrial reports for this, but I haven't seen any academic paper looking on this. And again, we will be using wire in pipe technology and nonlinear optimization-based estimation, which will be our contribution in drilling process. Okay, so second part of my work is about advanced deep water monitoring systems. So first, in this part, we are trying to automate the load balancing of the TLC platform. And if we become able to automate this process, the advantages of it will be increased drilling efficiency, because within drilling they can move the equipment on the drilling rig easily, so they will have less drilling time, and it will decrease the drilling cost a lot. And also, we will have reduction of cyclical stresses on the platform and increase pipe stability and tendon life. Again, because like the tide itself has changes over time. We will see it in next slide. and it decreases the lifetime of the tendons and the TLP platform, and improve resiliency of the platform balance and tendon tension control, because it is manual control right now, and with automating it, also we will be able to reduce the workload of the operators. Yes.
How do platforms support it anyway? No idea. Are they supported on the bottom? Are they floating and just kind of feathered? How does it work?
Yeah, I have this picture here. Let me show it. Sorry. Yes, here. So you see these platforms have cables. So each one of these legs consists of 4 cables.
So the platform is floating.
Yes, it's floating.
The cables just tether it.
Yes.
Okay.
Yes.
That's probably enough.
Yes. So
pretty important information.
yes. So
As you move on, I don't want to get lost.
yes. So it's attached to the down of the ocean using these cables. Okay. So for this project, we will be using fiber optic sensors, and it is advanced technology, and I used it in my internship too. And the fiber optic consists of a core and a cladding that is over it. And when they send the wavelengths through the fiber, and this fiber core, it has some here it has reflective indexes that vary over the length, and because of the germanium doping. And so because of this feature, when they send the wavelengths here, some of it gets reflected. And as the temperature change or as the strain value change, the value of the wavelength of this wave changes. So using that feature, we are able to measure the temperature and also stress on the using these fiber optic sensors. And they have advantages to other sensors, that they are water resistant, they don't need electric current, and also they are immune to electromagnetic interference. And they can measure pressure, strain, temperature, and vibration, and they have high strain sensitivity. So, as I said, the change in wavelength depends on temperature, actual strain, and also hoop strain. But the strain itself depends on temperature too, so we need to compensate the temperature effect. And for that, we use pure temperature measuring sensors or zero strain temperature sensors. That this is better than the previous one. So we compensate the temperature effect, and we just find the strain value. So this is some of the equations that I use for finding the temperature and strain values. I just show them here to you, but the wavelengths, as you see, it depends on temperature, and also it depends on the strain. So the results that I have had so far, I've worked on this project, most of them some of them are in my internship and some of them here. So this is because the first part of the control system is data acquisition software, and this software I designed using several different software and programming languages, and the main one is Python, and we have 3 different interfaces, and one of the interfaces is web interface that I show here, my web interface. So as you see, this is a TLP, and the load values that we convert the text to loads here. The load values change over time. So this is a 24-hour period, and as you see, they have 2 cycles every 24 hours.
You can see wave action there, and you can also see tide action.
Yeah. So this shows that it is kind of dynamics, even the tide.
You're kind of surprised, when this is the first time a system like this has been installed on the west coast of Africa. But you're kind of surprised when they first put it on. They saw things like boats docking up to the platform. We went down to what's going on with this, and they said, oh, it's just 10 minutes ago, the boat docked the platform. Or when there's a storm, you get to see that. Or they have in the summertime, they have whales that come into that area and actually remove their barnacles by scraping with the tendons. And so you could possibly see that as well. So, just a lot of things that you can see with these, it's very sensitive sensors.
Yes, they're very, you see, even for each hour, they are very sensitive and they change over time. So if we can as automation system, we will be able to smooth this and increase the lifetime of the TLC. So for my future work, I'm thinking of automating this process, and for this, I will, for my manipulated variable, I will have tension leg length as my manipulated variable because it can be changed using their equipment, and also the ballast tank water levels, and changing the water level in that, again, we can affect on the loads on each tendon. For my control variable, it will be the balance of the all loads and also the angle of the platform. And also my disturbance variable with the wave will be the wave action because it can be measured. So this is the model that I've proposed, but in future, like if I can find a better model, I will replace it. But so far, I think that this can capture the dynamics. The total load on each tendon depends on the load from the wave action, load from the platform itself, and load from the ballast tank. So the load from ballast tank depends on the water level on it, that it can be changed using the water pump, and the load from the platform depends on the rig weight on each side divided by 4 times on the angles that the platform has. And these angles depend on the length of the each tendon. So using this model, I will try to automate the balance. And again, this is the control structure. I am thinking about it. So like the data from the data acquisition part that will be loads that come to observer. Observer here will be simpler than the previous part for reading. Then I will have my controller, and wave action will be disturbance variable, and then tension load set points that I will try to balance. So the brain of our controller will be like this. First it should recognize the problem. For example, if it loses the balance, the controller will attempt to know which corner of the TLC platform needs higher load and which corner needs less load. And then, based on that, it will decide whether the change of the load should be changing the water level in ballast tank, or it should be through changing the tension leg length. So, for example, if it needs high load changes, use changing the tension length. If it is less, it uses the ballast tank pump. And then if the last part is the action, it will estimate, it will find the best values for these manipulated variable, and it will implement it for the platform to gain its balance. So for my conclusion, for the first part, I can briefly, if I can conclude, we say that integrating the drilling rate and pressure control together along with using wire prop technology, we will be able to increase drilling efficiency, and also we will be able to better managing the drilling rate safety during abnormal events. For advanced deep water monitoring systems, we say that using advanced fiber optic sensing technology along with integrating a controller system to the platforms, we will be able to ensure platform stability on dynamic basis. Because like this part, the balance of the platform is completely manual right now. So for my timeline, I just said that my goals have 3 priorities. The green ones are my first priorities. That's, for example, designing the multi-predict controller and also estimated using APMonitor, and also heat detection, and also having the comprehensive controller will be my first priority. And also for the advanced deep water monitoring, again, data acquisition and controlling the loads. Second priority will be I will do the same thing. For multi-predict controller, I will use the MATLAB and MATLAB solvers. And for nonlinear estimator, I am planning to use Kalman filters on that part. And my third priority is adding fault tolerance for vibration and also stick slip conditions. That I will do that if I have extra time. And in here, I would like to thank Astro Technology and also Hess Corporation for supporting my work. And thank you all for your attention, and I'm looking forward to your questions. Thank you.
We'll open up for some questions. Let's start with our online participants first. Can you guys still hear me?
Yeah.
Okay, great. So any questions? I'll start with Dave. Do you have any questions?
Well, yes. You know, just a question about you know, like calibration and you know, what kind of steps, Riza, are you using in order to calibrate the sensing system, considering that we put a monitoring device on after the fact, and we don't really have a zero state of stress defined? And so, what steps can you talk about that just for a minute? What steps you've taken in order to get an accurate calibration?
Okay, so let me go ahead and just repeat the question. Dave, you're a little bit quiet, so I'm just going to repeat it for the people in the room, and let me make sure I got it correctly. So you're asking for thoughts on calibration of these sensors, you know, especially for sensors that are installed on existing systems. What techniques or methods do you use? Is that right?
That's correct.
Okay.
Okay. So for the part that is data acquisition part, and also for my load control part, we need to calibrate our component, because here when we install our sensors, the load values that are reported with them, each of them has its own load value. We need to calibrate them to a certain baseline, and also because we install these sensors using clamps, its sensitivity changes because clamp changes the sensitivity of the sensor. So we need to also change the sensitivity. So for calibration, I have two parts. I have a sensitivity part, and also I have the calibration value itself. So the steps I do for calibration is that first I have to change the sensitivity value, because they have their own load cells on the platform. We get the exact values from them, and by looking at the range of the change of load from the load cells, I can find the best sensitivity factors for each sensor. So here you see that the sensitivities are almost the same for all of the tendons here. Then after finding the sensitivity value, I will have to find the best calibration value. So for example, if the value that is being reported by their load cells, which for example is 700 kips, I just have a additive part to my model, and I give it to the software, and software, by looking at the exact measured value, it finds out what the additive part will be. So for this site, I have had hundreds of lines of codes for this, and it's just when you go into it, it's a little tricky. And okay. Yeah, but now it is done, and we are able to calibrate it easily, very easily.
Okay, good. So, Dave, any other questions?
No, that's good. Thank you, Riza.
Thank you, Mr. Brown.
Okay, let's see. Mustafa, did you have any questions?
No, thanks. I enjoyed.
Okay, Mike, I'll open up to you now.
Yeah, just a couple of quick ones. First of all, a brief comment. So this was a nice piece of work. I like the fact that you're using wired pipe technology so you can get continuous measurements. And I might add, one key advantage of wired pipe, in addition to the very large bandwidth, is the fact that it provides measurements at all times with mud pulsing. If the mud is not circulating, you're not getting anything, and there are certain critical situations where the mud is still, when you haven't broken the gel yet and the mud is not flowing, and you cannot get measurements just because you have no pulsing there available. So you have some great capabilities there that you can capitalize on. Now, quick question also on what was presented. It was a very well conceived plan. Now, there was a reference made to the rate of penetration, which usually is a target for maximization. You don't want to keep it at a fixed value. Rather, you would like to make it as large as possible. And the idea is if you increase weight on the bit, ROP increases until you reach the founder point, beyond which any additional weight is going to create cuttings that cannot be removed, and you jam everything, and essentially the ROP decreases. Is this something you intend to include in your studies at a certain point? Before letting you answer, let me mention that this is a broad subject. It's not one where a simple single answer can be offered of the type, yes, I'll do this, I'll get the problem solved. It's something that requires an entire program that would identify where the founder point is, how to make sure that you go there, but you can exceed it robustly and so forth. But nevertheless, it's worth perhaps thinking about that. So I would like your thoughts on whether you intend to include that in your optimizations.
Okay, so can everybody hear the question, or do you want me to repeat it? Okay, so let me just repeat it briefly. Mike mentioned the rate of penetration is one of his targets or control variables he's trying to change. And in industry, you typically want to maximize that with the highest rate of penetration to get down to your formation the fastest. That you sometimes reach that boundary as you increase the weight on bit, your cuttings become more and more so you can't remove them with your mud circulation. So, you know, you asked about Riza's project, is he just trying to control to a value, or is he trying to maximize it? And his observation is this is a really big problem. It probably takes a whole program of work, you know, versus a project. So is it realistic for Riza to work on?
Yes. So, first, yes, you're right. Like I've seen projects have been done just on rate of penetration itself, like PhD project on rate of penetration itself, and again, I've seen PhD projects on pressure control itself. So that I am combining them together, more work than the others. But what I am doing here, I will have more simplifications for my work. For example, the researchers try to estimate the constants here, and if I see that would be problem, I will just use the constants that they have found from real-time optimization. So I will first, for example, if we want to use this model, we will first run a real-time optimization, find the constant, and then feed it into our controller. And then for Dr. Nicola, yes, rate of penetration I've seen in articles. It's not just maximizing it, because there are like other factors affecting it, and I don't have them exactly in my mind, but it has some constant that can be higher than a value and it can be lower than a value. And also, the goal of the researchers most of the time is minimizing the cost using the rate of penetration. So they put their goal on minimizing the cost rather than mostly maximizing the rate of penetration. So for my work, what I am thinking is that I will put constraints on rate of penetration, and one of the things that we want to show the idea that we are able to control the rate of penetration value, to change it to any value that we want with this integrated controller. But
as long as you are within the bounds that allow you to do this, right?
Yes, I will put the constraint on rate of penetration for doing this one.
Yeah. Okay. Sounds good.